I now want to look at defining a plane in 3-space. To define a plane, I'm going to need a point in the plane. I'm going to call this x0, y0, z0. And I need some vector that's orthogonal to the plane. This is usually denoted by n. It's known as the normal vector, and I'm going to call it ABC. So if I have any arbitrary point P in the plane, x, y, z, I want to consider the vector between my point that I know and this arbitrary point. So if I call this first one P0, I want to know the vector that goes from P0 to P. This is x minus x0, y minus y0, and z minus z0. Since n, my normal vector, is orthogonal to the plane, by definition, the normal vector dotted with this vector in the plane is going to be 0, since a dot product of 0 means you are orthogonal. So I can rewrite this as ABC dot my vector x minus x0, y minus y0, z minus z0 must be equal to 0. The definition of the dot product says I multiply things in corresponding places, so a times x minus x0, and I add the pieces. So plus b, y minus y0, plus c, z minus z0. And this is how I can find the equation of a plane. Most of the time we prefer to simplify this and write it in the form ax plus by plus cz equal to d. Let's consider a plane passing through the point 1, 3, 7 with normal vector -3, -2, -7. Using the equation, we use the normal vector, x minus the x-coordinate, plus the normal vector, or in this case, plus -2 or -2, y minus the y-coordinate in the point, and then we do the normal vector, the third component of the normal vector, z minus the z component of my point. And this must be equal to 0. Distributing, I get -3x plus 3 minus 2y plus 6 minus 7z plus 49 equal to 0. We can also write this as -3x minus 2y minus 7z plus 58 equal to 0. Moving the 58 to the other side of the equation, we'll put this in standard form. We have -3x minus 2y minus 7z equal to -58. So here is the equation of my plane in standard form. Another way to define a plane is having 3 points in the plane that are non-collinear, so they don't lie along one line. We'll call these P0, P1, and P2. We're going to start by creating 2 vectors, one going from P0 to P1, and one going from P0 to P2. So I have these 2 vectors, P0, P1, and P0, P2. We need to find a normal vector. So we need to find a vector that's orthogonal to both of these vectors, so that it'll then be orthogonal to the plane. By definition, the cross product of the vectors is orthogonal to the vectors. So once I find these vectors, I can take their cross product to get the normal vector. I can then use that normal vector in any one of my 3 points to find the equation of the plane. Let's consider a plane passing through the points 5, -6, 2, -1, 0, -5, and 3, 6, 3. The first step is to create 2 vectors. I'm going to start by going from the first point to the second point. So I would subtract -1 minus 5, that's -6, 0 minus -6, that's 6, -5 minus 2 is -7. Next, I'm going to look at going from the first point to the third point. So I have 3 minus 5 is -2. 6 minus -6 is 12. And 3 minus 2 is 1. So now I have my 2 vectors. And I need to find their cross product. To find the cross product, I start by ignoring the first coordinates. So I have 6, -7, 12, 1 times I minus, ignore the second coordinates. That leaves me with -6, -7, -2, 1 times j plus, ignore the third coordinates. -6, 6, -2, 12 times k. This is 6 minus -84, I minus -6 minus 14, j plus -6 times 12 is -72 minus -12, k. This then simplifies. 6 plus 84 is 90i. -6 minus 14 is -20. The extra negative makes this plus 20j. And -72 plus 12 is -60, or -60k. So my normal vector is given by 90, 20, -60. Since the length of the cross product does not matter, the length of the orthogonal vector does not matter, only the direction matters, I'm going to divide by 10 to get the vector 9 to -6. This will still be orthogonal. I just kind of shortened the vector to make it a little bit easier to work with. Now that I have my normal vector, I'm going to use my first point. I have 9 times x minus the x coordinate plus 2 times y minus the y coordinate minus 6 times z minus the z coordinate equal to 0. Distributing, this is 9x minus 45 plus 2y plus 12 minus 6z plus 12 equal to 0. Simplifying, I get 9x plus 2y minus 6z minus 21 equal to 0. And moving the constant over, 9x plus 2y minus 6z is equal to 21. There was nothing special about my first point. If I would have used the second point instead, I would have 9 times x minus the x coordinate plus 2 times y minus the y coordinate minus 6 times z minus the z coordinate is equal to 0. This simplifies to 9x plus 9 plus 2y minus 6z minus 30 equal to 0. Or 9x plus 2y minus 6z is equal to negative 21, or positive 21 rather, which is exactly what I had before. So which point I pick actually does not matter. I'll still get the same equation at the end.